We're going to start with the first keynote. It's actually my privilege and also my great honor to introduce today's keynote speaker, Professor Saman Amarasinghe from MIT. Aman is actually widely considered as the leading expert, right, the leading researcher on high-performance domain-specific languages and also compiler design. Now, Saman and his group actually have made so many groundbreaking contributions, right, and also developed so many widely used tools and also languages. Just to name a few, right? Maybe some of the recent ones like Halide for image processing, right? Streamlit for stream computation, Taco for sparse processing, and Graphic for graphics workload, graphic analytic workload, and also OpenTuner for this extensible auto tuning. These are just the recent ones, right? I can keep going. I actually think that this is very timely, right, for Saman to come to the FPGA conference and share his insights, right, on domain-specific programming, because we all know that this community, right, our community, has been working really hard to make FPGA easier to use for domain experts. Okay. So I'm really honored to have Saman join us here, and please also join me in welcoming Saman to the stage.
Thank you so much. Thank you for inviting me. This is, I think, one of the first in-person conferences I'm going to after a long time. So it's kind of after playing Zoom for all these years, so it's kind of strange. So again, this is not my home community, but I hope I'm going to talk a little bit on from the compiler side. And I hope this will inspire some of these people, some of you, to basically get into this area of structured data. And I think it's a very ripe area, especially for FPGAs. So large part of it will be how we can manage it in a nice way within a compiler. So if you look at the world, what we have built over last 50 years, we have built a world for dense. So if you look at things like hardware utilization, if you do something like matrix multiply, we can get top roofline performance, 70, 80, 90% of utilization of hardware. Why? Because over last 50 years, we have invented so many cool hardware features just looking at dense data structures. Prefetching, branch prediction, caches, all those things work beautifully when the data is dense. On the software side also, even the first programming language, FORTRAN, dealt with dense arrays. And from then onwards, compilers, libraries, all those things really focused on dense, and we are really good at dense today. How about sparse? Sparse is interesting. If you look at hardware today, stock hardware is really, really bad at sparse. So something like PageRank doing a sparse matrix vector multiply, you can end up with cache miss rates over 40% because our hardware is not ready for that. So you have to do some extra work to make today's hardware work in that. How about in software side? There's nothing. There's no abstraction. If you want something sparse, you have to write it from scratch in a language like C and deal with all those things. There's no nice abstraction there. So this is the world we live in. But if you look at the world of data, it's mainly structured data. There's a lot of data that's sparse, then we can take advantage of sparsity. There's a lot of data that has replicated value, run length, that you can basically take advantage of things like this video has a lot of replicated values in here. And also there's a lot of data that has symmetry. So data is not just one gigantic blob that you have to represent everything. There's a lot of interesting structure you can take advantage. So let me give you an example on sparse data that I will talk a lot about today. Sparse data is not new. Data analytics, a lot of data is sparse. Machine learning these days is getting a lot of sparse data. And even for last 40 years, lot of science like meshes, simulation, lot of things dealt with sparse data. So we are used to sparse data. To give you an example in data analytics, let's look at Amazon product reviews. What does it mean? So what that means is you can, oops, can you see? Okay, yeah, this blinked. So if you look at Amazon product reviews, you can think about this as a three-dimensional tensor that has every product Amazon sells, every person who buy a product from Amazon in another dimension, and every word that probably in the dictionary that is used to write the reviews in. So this tree tensor, you can represent it as dense. If you represent it using dense, your storage is going to be size of the entire Amazon data center. But it's not that even though I buy a lot from Amazon, I haven't bought everything from Amazon. So I only buy a very small fraction and I probably don't write that many reviews either. So this tense is extremely sparse. And if you only represent non-zero values in there, it will fit into your laptop. So in these kind of cases, you have no choice but to take advantage of sparsity. So how does sparsity work? So let me give you some performance information. So this is running on a CPU. So as data get dense and dense, you have more and more computation to do. So if you do just normal matrix vector multiply, it doesn't matter how much sparsity, just pull one matrix, you are multiplying and get flat performance. If you use a sparse data structures and sparse matrix vector multiply, what happens is if the data is very dense, the sparse data structure is complicated, the sparse matrix vector multiply has overhead, so you are slow. But at some point you break even. And then if you have a lot of sparsity, you have almost linear speedups as sparsity increases in here. So if you go to something like sparse matrix multiply versus gem, the break-even point is lower. So that means you need to have more sparsity to do that. So you think, okay, that requires a lot of sparsity. In some cases, yes. So if you look at this range of density in here, SPMV fit in one place, SPMM sit in somewhere, and something like neural networks right now is sitting in the range where SPMM performance is going to be break even or a little bit better. So we are sitting at that range, that break even point at this point. But if you look at this ultra sparse area, there's a lot of interesting applications that has sparsity much larger than anything you see in right now on basically machine learning type applications. Some of these things are crazy sparse. So I will give you an example. LiDAR. A LiDAR application represents in here 3 dimension 8 by 8 by 8 a cube of data, but only about 300,000 points in each LiDAR snapshot you get. So the data density is extremely sparse. And if you try to put it in a dense matrix, that's not going to work. So these kind of things you need to represent in a sparse way in here. So why isn't everybody using sparse all the time? Because sparse data representation and code is a little bit more complicated. So here's a very simple dense 3 tensor multiplied by a vector code. Even an early undergrad can write this code, no big deal. But now this 3 tensor, if you use it in a sparse format like this sparse fiber format in here, the code gets a little bit more complicated because now we have to iterate over this sparse data structure. And also if the vector is sparse in a compressed format, now the code is a little bit more complicated. So as you add more sparsity, it gets complicated to get the best performance. And if you are adding 3 tensors together and with 2 different formats, to get best performance, you need to write code like this. So that is a lot more complicated in there. So this is why this is hard. The problem is, right now, the only way we know how to do that is treat each of these expressions separately. But there's a lot of these expressions. Linear algebra alone has many, many important expressions. Data analytics have another set. Even quantum chronodynamics have a different set of expressions. So if you're trying to go write each expression separate, it doesn't scale that well. Just to give you a simple example, sparse matrix vector multiply. This is supposed to be the bread and butter of sparsity. There are many different small variations that you need to write because if you want to get the best performance, you need to have specific generated code for that. In fact, OSCE library alone has 282 versions of sparse matrix vector multiply. Why is that? Because sparsity Unlike dense, there are so many different representations. In dense, you can only have row image or column image, and sparsity. You can have CSR representation for things like thermal simulation, DCSR if you have huge amount of sparsity representation, things like web matrices, block CSR if you have blocks in here, coordinate representation, data analysis, go on and on and on. Different representation makes sense because data, the structure of the data is a little bit different in all these problems, and some representation take full advantage of data, things like blocks, things like diagonals. And then there are more and more representations you can add. And then also, you need to write different piece of code for each architecture. So this is great if you are a library writer. You have full-time employment lifetime because you write all this code. But it's not good way to scale and make this code available. So what we have done, I'm going to talk a lot today, is we built this system called sparse tensor compiler, Taco. It can take any tensor expression written in INSUM format, so any expression in here. And then each of these tensors we can represent using most of the popular formats out there today. And we also have a scheduling language I'll talk about to give it a little bit support to generate good code. And today we can generate basically C code for CPUs and also CUDA code for GPU. So that's the system we have built today. So how does this work? So we can generate code for all these things, but it's very hard to compare because most of them don't have really good implementation. But library writers have written good implementations for common kernels in here. So I will choose 3 common kernels. So sparse matrix vector multiply, if you look at our performance, shorter the better. So Taco is comparable with Intel MKL, which is Intel has put a lot of resources, hundreds of engineers in that project, optimizing these library codes, and we are actually generating code very similar to that. So this code, STDMM, we also get the best performance compared to Eigen, that is the closest performing code in here. And this MTTKRP code also, the best performing code is a different library, and we are getting good performance. So when you look at this graph, you will realize something. Sparse matrix vector multiply. Yes, we get few factors of performance. That's because we do parallelism, but the performance improvements is not that high. But STDMM and MTTKRP has this huge performance improvement. What's going on here? And in fact, if you want as a FPGA community to take one idea home, this would be it. So let me explain what's going on. So if you look at this, Taco and Eigen, what they have done is they have created a single routine that will do the entire STDMM. But STDMM, as I'll point out, can be also done by doing individual binary operations and combine them together. And what happened when you do that? So when you look at STDMM, is it has 2 different dense matrix multiply. There's huge amount of code out there to do dense matrix multiply. In fact, there's a lot of hardware that will also do dense matrix multiply very, very well. So you can use that and get the best performance dense matrix multiply. Then I will get 64 inner products here. Then I'm going to multiply it element wise using a sparse matrix. So to get this value, I have to actually get this dot product in here. But what do I need to get to this value? Nothing, because it's multiplying by 0. So what we have done is doing this dense matrix multiply, created in this case 64 elements and thrown 54 away. Only 10 things survive. So this is one place where you need a custom computation for the entire operation. Libraries do this element-wise or binary operations that you can cascade together. In a dense world, you might get a little bit of cache performance hit by just cascading things because you might go back and forth to memory. You might get 10%, 25% slowdowns by doing that. But in sparse world, it is asymptotically slow if you try to do that. So this is a place where given a complex expression, generating the full expression, right, we are doing in software. You guys in FPGAs, if you can do it in hardware, you will get asymptotically better performance than if you have fixed hardware that will do these binary operations and you are trying to cascade them together. So this is a very interesting opportunity that's much more different from than dense worlding. So I have feeling this is where I want to see a lot of FPGAs coming up, because they are given my expression, I should be able to generate something that will take advantage of that and have this kind of meaning. So what we can do is we can generate this code. In fact, that is why uBLAST is slow. uBLAST has really good binary set of operations. So they did SDDMM by combining a very fast matrix multiply with their element-wise sparse dense multiply operation. And so they are doing way too much computation. Whereas I can hand wrote one specific function to do this, and we generated. So next thing, what I'm going to do is go into little bit our compiler magic. Say, how is compiler achieving this? How can we generate that? The idea there is handwritten is each thing is separate. In a compiler, what you have to do is come up with some kind of a unified way that we can handle everything. So it's all about coming up with right set of abstractions. So that's what we are going to do. So I came up with 5 different things we are working on. So first, if you look at irregular data structures, these things, when you look at, there are tens of different formats, each has its own paper, it looks very different. And what we had to do is come up with a representation that can represent everything. So let's first look at these kind of data structures. What does this mean? So I'm just doing a little bit of a primer in here. So if you look at a dense matrix in here, if you look at this, representing this as a dense matrix, you just line up in memory. This is how it is. This is great. This is our dense representation. So to find a value, I can easily calculate where the location is because I have a formula and directly jump and get that value here. But the problem in here is I am wasting a lot of my memory just representing zeros. I don't want to do that. So I want to compress them together and only keep in memory non-zero value. This is great. But now, how do I find what that value is? I don't know. So I need to give some metadata. So one easy way to metadata is also keep an array of row coordinates and column coordinates, and then I can look at the coordinates and get to that value. That's a easy way to do that. So this is called the coordinate format. And this is very commonly used format. Then the community long time ago realized in the coordinate format, for the same row, I'm replicating the row coordinate multiple times. This is inefficient. So therefore, they came up saying just represent the start point of the next row, next column, next row, and that is called compressed sparse row format. That's the most popular format today. So this is the format most sparse matrix summation. So this is nice. So now, if you have these 3 tensors, normally you can get a paper that's saying here's the 5 different data structures that can represent this tensor, and every of these things has very different thing, and that's very cumbersome because everything is different. So we looked at close and realized, look, even those 5 data structures, you can figure out, separate these data structures to dimension by dimension. So you can say that first this get the slice coordinates, row coordinates, and column coordinates. Furthermore, each has a pattern. The slices are dense, so only say how many numbers are the length of that. The next level seem to be compressed representation that read these 2 different data structures, something like CSR read that. The last one, basically, for every value that come from the above, I only have one value going down. So I have a singleton code in here. So by doing these specific representations, we realize we can abstract out many different representations. So I have these 3 dense, compressed, and singleton. So here's our original make. And if I get a dense out there and a compressed next, I end up with the CSR format. So I can build my CSR using these simple 3 building blocks. And if I use compress outer and singleton inner, I end up with the coordinate format. In fact, what we found was using these 3, not only these 2 formats, many published formats we can basically build out of that. So what that means is we have very simple building blocks and a simple methodology to build a lot of these existing formats. And then if we have 3 additional level formats, we can basically get most of the common formats people use today. So now we have a way to build out this seem to be independent different formats out of a very simple formula and simple set of level formats together. That's great. This is what we deal with sparsity. Can we take it even further? So here's a simple 2D matrix in here. And if I do it using my compressed level format, I get a representation like that. I don't have to represent zeros. Series are implicit. But if you looked at this closely, what you realize is there's more ones than zeros. So one thing saying is, instead of making zeros implicit, tell me what value is implicit. So what they are doing is, it's called a fill value. You say, aha, I just want to make one implicit, and I will get a little bit of a smaller representation. Then if you look at even more closely, what you realize is this matrix has lot of different runs of zeros, runs of ones, runs of sixes. So we can come up with even a better representation similar to run length encoding. What it says is, each value for the next empty implicit block, you replicate the last value also. So you just get runs in here. So what that means is, if I have the last value, I have 1, the next 2 value was implicit, the next 2 values are ones. The last value I saw was a 6. If the next 4 values are implicit, replace it with 6. So then it's not just sparsity, it's not only ones, I can have any basically run length encoding. This is really interesting. So what we have done right now is unified the concept of sparsity to basically lossless compression. Lossless compression use run length encoding, but now you can use the same framework with small extension to basically get lossless compression. This is really cool. So here's 2 different examples in here. One is MRI image, other one is a cartoon in here. And if you use dense, you have no additional compression. If you just use sparse, if you just compress out zeros, you get little better compression. But if you do run length encoding, you get really, really good compression. So this is great. We can actually get compression, but here's an interesting killer in here. In the compression community, what they do is they do compression to store and move data. But every time they want to do computation, they expand it back into the full dense world and do that. On the other hand, we do sparsity to actually operate directly on sparse data. So can we operate directly on compressed data? We can. So what we can do is, in fact, we can do this thing, lossless compression, directly work on compressed data. I never have to expand it out for a lot of computations. And in fact, we can get really nice speed ups by just basically operating directly on compressed data. So here's something that I think we can take from a sparse community to a new community and show them something that they haven't done before, and do it in a way that's not that different from what they're doing today. So there's some really cool stuff we can do. So another interesting thing is, if you have a dense data structure, when you allocate that, you allocate a location for every value of the data, even though zeros or 1. So I can add or change anything. On the other hand, in a sparse data structure, I only allocate values for all the non-zeros. How about if I get a new value that's a non-zero? I modify my matrix. I am in a little bit of a trouble. Let me show something. This is in fact a log plot. So higher is much more slower. So this is doing page rank computation on bunch of different size CSR matrices. Page rank is a pretty complex computation that involved the entire matrix. But now I said, okay, get that matrix. I want to add one value into that matrix. It's more expensive than doing page rank, because adding one value into CSR means I have to completely restructure, recopy the entire matrix and rechange a lot of things in here. So this is really sad, because if it is dense, adding one value is order one operation, boom, just go find the location and modify something. Couple of cache means that's all that you're going to get. Not here, I'm copying everything. So this is not working because there are a lot of interesting applications, in fact, that I want to basically do modify the data. So think about Facebook friendship graph. It's a sparse data structure. If you say I add a friend, Facebook say no, that's very expensive. You can't add friends. That doesn't work. you should be able to add a friend easily. And so for that, you need to get more pointer-based data structures. So what we need to do is get some kind of recursive pointer-based data structure. So we came up with this special language to basically describe those data structures. So I can just have a simple linked list. I can do a block linked list in here. Why different data structures? Because depending on amount of insertions we do, type of computation we do, different data structures wins out. So there are more complicated data, variable block size data structures, C trees, B trees, all these data structures. Now we can generate, and also we can generate iterators, optimal iterators that go over the data structure. And this is really cool because now we are almost getting near like a database community in there, and it's all automatically generated. So this is how we tame our irregular data structures. Now we can generate them using very simple concept, very simple set of primitives. Next thing that interesting is iterating over these data structures, sparse data structures. So for that, we came up with this notion called iteration graph. So assume I have this very complicated 3 tensor in here. If it is dense, it's very easy to iterate over this. I can basically go and say, find my location, calculate the location, directly look up and go, but you can't do that here. There's no order 1 random access. I can't order 1 access there. To get to a location, we'll say 202. First, I have to find 2 in the first compressed row, find where it is in the next one, find that value, keep going down, searching to get that value. So locating any arbitrary value is very expensive, but what you can do in these data structures more easily is find the next value, go to the next in there in a certain order. If you go in IJK order, I can go to the next value in the order 1 fashion, find the next non-zero values. So that is how you need to use this data structure if you trade. So that creates some interesting problems. So assume I have to do this computation. How about if it is, so they have a 3 tensor in here. How about if it is dense? I have a dense iteration space. I can do IJK in here. And CK is 1 dimension, but if I want to co-iterate, I can think about it's getting replicated in all the dimensions. And now I have a very simple 3 exact iteration spaces. I can merge them together. I can co-iterate. So every time I get IJK value, I can both get a B, IJK and CK at the same time. I get the computation. Not so simple in sparse. So this BIJK, I have to iterate on the order IJK order. That's why that you get the order 1 next. Here's 1 dimension. It's not that much of an issue. Now, if I'm going to co-iterate over these 2, I need to merge these things. And then because I am doing a multiplication, I have to do intersection of these 2 spaces. So this is what I get. And then, of course, I produce the outputs in I and j dimensions in here. So interestingly, if I have this iteration graph, which is and there's no cycles, I can easily generate code. If there are cycles, you have a problem. I can't generate code. The interesting thing here is for every computation, we can easily create these iteration graphs. It's a very mechanical process to create that iteration graphs. And then we can use iteration graphs also mechanically generate code. So here's the iteration graph of previous one. Assume A is dense, B has a dense outer and compress next 2 dimension, C is compressed. So I go to generate code, I go to the outer loop and say, aha, it's dense. It's only B1 in here. I can generate a dense loop. Then I go to the next one, J, it's B2. B2 I look up, it's compressed. I generate for the compressed dimension in here. Then I go to K. K is merging between the compress and compress, and I have to generate that code. And then finally I say, here's my computation. So this is how I generate code. Very mechanical. That's what compilers are good at, doing something very mechanical, and we figure out a way to do this mechanical. But then I hit something. This piece of code doesn't look that mechanical. It's a little bit complicated. The next thing I want to show you is how to generate code like that when you're merging something. And this is where this avoiding work comes into play. I will explain a little bit later. And this is what we call co-iteration for code generation. So let me explain it by using just 2 simple vectors, B and C. I am doing a dot product element-wise multiply calculating. So the interesting thing in here is, if I am doing a B and C, only values I need to compute is if both B and C has the same coordinating, everything else just goes away. So this is where you can get lot of unnecessary computation done, because you here unnecessary loads. You are loading entire B, entire C. Only thing actually participate is this intersection in here. So you can use this as intersection computation. And in fact, we can write this as this simple lattice. In both B and C present, do the computation. If either B or C runs out, because we are going monotonically increase, if one runs out, you're done, because there's no other, the rest of the other won't participate in the computation. So when for B and C, I can generate this loop nest saying while both B and C exist, I go iterate over next in here. And then if both B and C has the same index, if I find a index that both B and C have value, that's in that intersection, I have to produce the code. Otherwise, I don't do it. I just keep iterating over both of them. So this is how we generate code for a simple intersection. And then when either B or C runs out, I'm done. I don't have to do anything. That's this outer while loop. How about addition? Little bit more complicated. Addition requires union. So what that means is I have to do union, but I can rewrite this as saying intersection and all the leftover two side lobes of the intersection. And then I can put this into this lattice. And then here what we can say, if both B and C exist in my array, I'm two arrays going forward, I generate this loop in here. Then I have to generate code for the everything underneath of this lattice. So if I find a value that has both B and C, that means I actually have to do addition. But then if only B exists, I just have to copy that value. Or if the C exists, I have to copy that value. So that's what we have to do while both B and C exist in there, because everything it's all the values don't exist, only certain things because sparse. Then assume I run out of C. If I run out of C, I just have to copy rest of the B's in there. And if I run out of B, I have to copy rest of the C. So this is basically, again, given this lattice, a very mechanical way of generating code. Still, you can think about this. Now let something a little bit more complicated. B plus C plus D. I can still generate this lattice. It's not that difficult. But now, again, mechanically, I can keep generating this code. The code looks extremely complicated afterward, but it's, again, mechanically generated. So I generated this piece of code, and this is the best code you can get, but the compiler can do this. There's no magic in here. We can even go further. Assume I say D is dense. What that means, you can't run out of D. So that means I change my structure because D goes everywhere. And what that means, my lattice changes because the D is the last element you would see. You can't run out of D before. And my lattice changes, my code changes. So now this is also the most efficient way of generating code if you have outer mode. So what this means is, given any tensor expression, whether sparse or dense, I can generate the most efficient piece of code in a very mechanical way. That's very useful that's very nice for a compiler. And this is just intersection and union, which is multiply and add. There are a lot of other operations we can still generate code for that. For example, again, here's the addition in here. But if you have XOR instead of addition, what that means is the middle part, I do nothing. If both B and C present, so I can just again generate code and say if both I and J are the same, don't do not anything, get rid of that line, and again that's the code I had to generate. So I can even get XOR generated. So this is very important because this is how I can get asymptotic wins. I can avoid generating code, doing computation, also doing unnecessary loads for these when I don't need, when the final result that doesn't participate because it gets multiplied by a 0 somewhere in the computation. So I want to take this one level further for more complicated data structures. So here we came up with this notion called looplets. Let me explain that next. So for last 50 years, the way we dealt with data is dense, and dense basically you go to increment, you go to next value, next value, next value, I1 plus I plus 1, I plus 1, I plus 1. That's how you go through data. And we know how to generate code for that. No big deal. And if you have multiple dense arrays, I know how to generate code. From the time FORTRAN, we knew how to do this. So far, what I introduced is, how about if I have another compressed data structure? Now we have this combination of both dense and compressed. If both are compressed, I am doing this 2-finger merge. I'm going looking at the next India. But if only one is compressed, I can iterate over that using next, and I can look up into the dense one. Because if the next index is, we'll say in here 2, I can look up 2 in the dense one. I can immediately do that. If the next index is 5, I can look up 5. So what I can do is I can do a next lookup and generate code for that. So by doing that, this is how Tahoe will generate code for these combinations. But the interesting thing is there are a lot more interesting and more complicated structures out there. It's not just compress and dense, run length, block, variable block, many much more interesting things. So how do you generate code for this? And this thing doesn't scale that well. So what we figured out was, can we explain an iteration of any of these things using these 8 different simple concepts? Lookup, run, spike, on. So just to give you a very high level concept, so here's a data structure I will represent. I would say anytime I have a run, and that means runs of something, and then a scalar, different scalar, it's called a spike together. And something like you can have a bunch of different spikes together that has a run and a scalar. And then if you have the same thing repeated multiple times, you have a stepper for n times doing same thing. And if you do different things, it's a pipeline. So certain ways to combine operations. So you can have a part of array just doing sparse, part of array dense. So you can have a spike, and a run for a dense one. Or you can do some things like that. So you can combine these things into building a lot more complicated things. And then for each of these types, we know how to generate code. We know how to generate code for run, how to do for lookup, how to do a pipeline. We can generate code. And then we came up with set of rules to basically, when you co-iterate, how to optimize if you are doing 2 different things next to each other. It's a lot more complicated than what we do in Tahoe. But now I can have many different types of data structure. I can have ragged arrays, large length matrices, symmetric stuff, all those things, and operate over that and operate very efficiently. So this gives you ability not just do with sparsity, deal with many interesting types of structured data in a very formulaic way and generate the most optimal code out of that. So the last thing I want to add in here is how to optimize for parallelism and locality. So here, what we realize is compilers are not oracles. They always make mistakes. They don't know. So we need some human support. So we came up with a scheduling language. If you have seen Halide, it's very similar. So you have a loop nest. You tell them to do loop transformations and parallelize certain things, unroll all those normal Halide type things. You can tell and modify the loop and get really good performance. But that's one interesting thing that happened that we had to deal with separately. So normally what you do in something like Halide in dense library is you block. You take iteration, you break it into equal chunks, and you do loop transformations and stuff to get good cache locality. The problem here in sparsity is if you block, the block means you divide the iteration space into equal parts. You might not get a load balance chunks in here. So if you divide this in, we'll say 2 different chunks in iteration space, one chunk has most of the data, other chunk has nothing. So perhaps you might have to divide it in a different granularities, not exactly at the middle. And if you want to do an equal chunk, you need to actually divide in a way that's not really dividing. You have to divide like an interesting line within the dimension. So here, what we are talking here is either doing at the coordinate space, which is we normally used to do, and or the position space where the actual real data is. You got to figure out where you are dividing. So we do that. And I will give a simple example how we generate GPU code. So here's the simple SPMV code. And then I can go start doing these kind of scheduling command that keep transforming the code. I split it into multiple dimensions. And I call it block, warp, and thread. You might know what it is. And then I basically parallelize those things for the GPU. And then I can keep adding a couple of scheduling commands like pre-compute and unroll to get the best performance. And by writing really good schedule, we can in fact generate code sparse code that are very comparable to what what NVIDIA people have generated. They have really good, very high performance handwritten libraries. And our generated code also comes pretty close to that performance. Places where we lag is because they have actually changed the data structures also to be different than the normal CSR. And some of the data structures our current representation don't handle, so we don't get that performance. But if it is just loop transformations that get in there, we can generate that code, getting the performance that these handwritten libraries are getting. So schedule languages are great, but more people don't want to write this schedule language because they are complicated. They have to really understand the hardware in here. So what you like to do is have auto schedule. So what that means is I have a domain expert in here, and that person writes the tensor expression, and our tensor framework will take the input and produce the value. That's a normal form. But now we added this wrinkle that we have a performance engineer that look at the tensor expressions and come up with a schedule. So this is the part when you have a scheduling. So I have some very low level that actually had to do some optimizations. The problem is we want to hide Taco buried inside more complicated software. So you might want to do it something like NumPy or SciPy. So there the software is very high level. And now that performance engineer it's a really hard thing to do because they don't know what happens in the pipeline. And to have human very deep in the pipeline is really hard thing to do in this kind of software. So we want to come up with auto scheduler to replace this human. So one way to think about that is, can we do this before I have input that will work the best for every possible input in here? And here we came up a system that will identify asymptotically best schedule no matter what input is. Why is asymptotics interesting? So even let's look at a dense example in here. If you look at this dense expression, I want to do this expression in here. And I have two ways of doing that. I can do this all the matrix multiply and multiply by the vector all together. Or I can do matrix vector multiply, get a vector, and do another matrix vector multiply and get a vector. If I do the second way, it's order n squared. If you do the first way, it's order n cubed. So it matters how you order my computation in here. So this is what happens in dense. In sparse world, there are many different choices. If you make the wrong choice, you can be asymptotically worse. Loop fusion, also the formats. If you chose the wrong format, you can be asymptotically worse. So you have a lot of choices. It doesn't matter what the input is, you are asymptotically slow. So what we came up with the way, looking at a given expression, you look at all the different ways to I can schedule that. And of course, if you need more loop to compute, that's probably asymptotically worse because I'm doing more instead of n squared to n cubed. We won't avoid that. But even same depth, we look at how many data items I want to touch. If I am doing a union, I do a lot more work than I do intersection. So I will find the computation that end up doing intersections to be asymptotically better than things I do unions. By doing that, I can get rid of certain computations and find the best one. So what we are showing here is by doing that, we can get really good, almost asymptotically good performance. So the first one is the naive thing that will generate the blue one. And then we figure out asymptotically based schedule, and we'll get the red, the curve sitting in the bottom for a lot of interesting things. So here we generated something asymptotically based. But at sometimes the interesting thing about sparsity is each sparse tensor or matrix is different. How about if you tell you my matrix shape and the pattern to the autotuner? Can it do something better? So what happens is the autotune is now in the runtime, I look at the matrix here, I have a banded matrix, I have a blocked matrix, I have a very special type of a matrix, generate code that is optimized for this matrix. So this is what we did. So here are three types of matrices. One has these block diagonals, other has couple of diagonals, but there are some unstructured in the beginning. The third one is just random distribution of data all over the matrix. So what we want to do in here is choose a specific format for that data and also come up with the loop transformations to get the best performance. So what we can do is we can given a sparse matrix in here, And given the format and and the schedule, we can come up with a cost model to predicate the runtime. So we came up with this machine learning based system that basically predict the runtime, also machine learning model. And we have a program embedded, also machine learning model to figure out what the transformations are. And also feature extractor from the sparse matrix to figure out what features are. So I'm going to only talk about feature extraction given time. So if you give a sparse matrix, I can ask you to write all the features. How many non-zeros are there? What is the distribution? It's a power law distribution. A lot of interesting features I can extract, and I can tune from that to say what the right thing to do. This is cumbersome. So what people say is, you can treat this matrix just as image. Why can't I run a CN in the sparse matrix? But the problem was the sparse matrix was way too big to run a full pipeline. So what they did was they downsampled it to a smaller image and then run a CNN and extract that. This is great. This extract lot of global features, but lot of local features like block sizes get gone away when you do this downsampling. So if you have 3 by 3 blocks of a million by million matrix, when you do 128 by 128, you don't have that information left anymore. So we thought that we can do better. So what we have is we came up with this network that basically start doing a convolution at the outermost level. And then what we do is we do downsample to smaller and smaller matrix and do convolution at every level and feed that everything into a machine learning pipeline. And by doing that, we can basically learn a lot of features, and this seem to learn both local features and global features very well. And what we are showing here is given specific matrices, we can get really, really good performance. So what that means is sparse matrix vector multiply these right now, just to get 5% above MKL is hard, but we can get 2x for certain matrices because there are certain shapes and patterns we can take advantage of that, and we can do that. So right now, Taco is available in 3 different things. We have this library, C++ library that you can run there. We have it in Python. Sorry, went a little bit too fast. And then we also have this online tool that basically you can go log in, you can write to expression and write the formats, and then it will basically generate code for you. A lot of people use this to just cut and paste into their libraries the coding. So we have made Taco available in 3 different ways. And in fact, we are trying to make Taco now part of the Python ecosystem because some SciPy and NumPy do a lot of cool arrays, but most of them are right dense. And there's a thing called PyData sparse trying to use sparse data structures, but they don't have good code generation to get good efficiency. They are orders of magnitude slow. So we are trying to get Taco into that system. So let me finish by talking a little bit about hardware because we are in the FPGA community. So I believe sparsity is a really good channel for FPGAs for 3 reasons. Because most sparse data in a computation never get used. You bring the entire data structure all the way to the ALU and realize, oops, it's an intersection. I throw away 99% of the data. If I have a way to basically filter this close to memory and say, you don't use that data later, I can save so much bandwidth in there. So why bring these things? So today I'm just bringing so much data, throwing out 99% of it. So here's a really good opportunity to do near memory computation. Another thing is most systems today, data is a black box. It's just bunch of bits in here. I don't understand the data until I come very close to the ALUs in there or in the CPU. That's where I understand the data. But if I know the data early on in memory, I'm not asking you to do a full computation, have a full ALU in memory. Simple intersection, simple union, that's a very similar, almost a memory level computation, can save a lot of the things. If I can, and also if I can pack into cache line the data I need, there's a lot of interesting opportunities you can do that. Here's a place, again, FPGA community, because then you can understand more and more data structures. You can generate code that I think you can do really well by doing that. Third thing is, I think it's only FPGA, not just hardware, not just ASICs. I showed you something like STDMM. I need to generate code for the entire expression. That's asymptotically been in here. So I can't like stamp out, I can probably stamp out a sparse matrix vector multiply, sparse matrix multiply. But if you get SDDMM, I can't combine some of these things. I can get, I'm of asymptotically slow. So for each compound expression, if I can generate code, I can generate really, really good code. And I can get asymptotic. It's not cache line wins. It's not just 10% win. I can get orders of magnitude wins in many of these cases. This is a place I think we can get a lot of good performance. There have been a lot of work. If you look at the work that happens in some FPGA, certain things like ASICs, the beginning stuff basically did the one computation. And in fact, right now, NVIDIA actually made a commercially available thing that actually deal with a very simple sparse matrix multiply. So they have that for very simple sparse patterns in here. There are other systems that have done more complicated things. And recently, things like the Stanford and MIT SAM system is trying to do it for compiled generic INSAM expressions for many different formats, and they're building a CGRA ASIC to do that. But still, there's a lot of opportunities in here to do this code generation. I'm just going to say there's a lot of work in our group has done on that. There's a lot of papers. Just go to my website if you're interested. Beyond this, my group worked with a lot of different domain-specific languages for bioinformatics, graphs, compression. In there, we work a lot on vectorization. And recently, I am also looking at how to use machine learning to make compilers better. Compilers are still very traditionally built. Can you use machine learning to make creating compilers easier? So these are the kind of research I do. And if you are interested, you can go check out information from this website. Let me stop here and thank you everybody for listening. Oh, I didn't time by. Yeah.
Okay, thank you, Saman, for the great talk. We are a little over time, but I think we can take a couple of quick questions. So if you have questions, please raise your hand, and Muhammad will pass you the mic. Muhammad over there. Oh.
Thanks. Really interesting talk. So if you look at the traditional sparse data structures that you were mentioning earlier on in your talk, they're really useful in the setting where both the sparsity pattern and the values change between function invocations. But in the FPGA world, we're often trying to take advantage of the situation where the data values change, but the sparsity pattern stays constant. And it seems to me like the latter part of your work is really useful for that setting. Do you have any comments in around that situation?
Yeah, I think if you understand both the structure and the computation, you can do lot more, and you can in there. But the interesting thing is most of the time if the structure keep changing, then trying to compilers, at least you have to compile in FPGA, it's even worse because you have to do the entire through FPGA pipeline. That's not amortizable that easily. So if you have cases where same structure or small modification to structure survives across a large time, you can do a lot more. Yes, that gives you ability to do that. But what we have said is we can operate at every level. I mean, you have less information, you're less good. You might not get the best performance in there, but you can still do well. But if you can give me more and more information about the structure, I can probably optimize much better for you. Yes, I think that's a good question.
Thank you, Saman, for an excellent talk. So I would like to go back to your sampled dense matrix multiplication.
Yes.
That's the fundamental operation you do in graph machine learning, as you know.
Yes.
My two comments are, if you profile those kinds of codes, maybe about 70% of the time is spent on memory access. So I would like to see what kind of optimizations you do specifically from the memory system performance for these kinds of computations. And the second comment is that There are a lot of libraries available for that. If you have any comments to make on how these optimizations work compared with, for example, the deep graph library, DGL from Amazon.
So hold on. I was trying to get myself into that, but I think I went too far. I got too carried away. Where's my? So too many builds. Sorry. So I think the main thing that I think you guys have a paper that I think you guys have done a job done that is also make sure that I first look at B to make sure that I need that value in C and D, and I will only compute if it is that used in here. So I can take it one further, saying not just compute, I won't even fetch if nobody uses that. If that entire row is 0, so if that entire column is 0, I can even not fetch C a row, a column of C, a row on C or column of D, because I know it will never part of the computation. So I can even, if B is hypersparse, I might be able to do that. So the first thing everybody do is they fetch B and C and D, but don't do the computation. But another level you can do is I don't even fetch if I don't do. So I can keep pushing that to the boundary in C and D. Here, nice thing about C and D are dense in there. But if it is sparse, again, there are these choices of fetching in there. But the problem with sparse is to know which part is a lot more complicated because it's data dependent. So I have to go find things like that. So to reduce, there are a lot of cases where you can even reduce what you are switching from sparse. And in certain computations, what end up happening, using is the intersection or union of non-zeros. So if very early on in memory, I can do that and bring something. So for example, a lot of times we bring a cache line of values and only one value of the cache line is used. But in very early on, I can say, look, I'm only bringing I'm going to pack the cache line contiguous values, but values that I'm going to use later. So some of these computations, if I can figure out what survives at the end and who contribute to that very early on, if I can back propagate some stuff in the computations, only fetch these things, and I think I can really reduce my memory access. But that means the memory system or whatever sitting near memory has to understand a little bit about my data structure. It's not just a bunch of blobs. It needs to know I have indices in here. I need to look at some of these indices to figure out which matters. So if I can do that, but it doesn't mean I have to have a full ALU in there. I just need some comparison, some addition, some very simple operations happening there in near memory to basically do that. So I think there's a lot of interesting opportunity. I'm not a hardware person, so I don't know exactly which things would be easy to implement, but I have a feeling there might be some simple things you can do that can really, really reduce the memory that you're bringing in.
All right, maybe one last question.
Hi, thank you. Very, very interesting talk and great work. It's really inspiring. I have a quick comment. Could you go to slide 36? So I think in that slide, well, I put in this way, a lot of the sparse framework around assume that when they do the computation, they produce a dense output. And maybe that's fine for like ML workloads, but if you are in computational chemistry.
Let me get to my slide. Come on, my bills are too.
Very cool.
I'm slowly getting there. Oh, now going fast. Okay. I'm just, I guess, going 32. Sorry. Okay.
All right, this one. So I was saying many sparse framework assume that A is dense, stored in dense format. And maybe for like ML, it's fine, but for like quantum computational chemistry, that thing is then multiplied by another dense matrix. So you create densification problem there.
Yes,
so I was wondering if
yes.
you know plans to support sparse outputs.
This is why I mean you can do two things. There are convolutions where only non-zeros are the non-zeros the input in there. I mean, that's what we did in VACO also. But the interesting thing is output is still a pain for us. Basically, there are only three things we can do today. One is just make output dense, easy. Other thing is we can replicate the output with the sparse structure of one of the inputs. So if we are doing a sparse matrix, dense matrix, add or something, the sparse matrix is the output. In SDDMM is the same thing. The basic output is the sparse format of the sparse matrix. That's easy. The problem is if the output format keep changing, so this data structure is very complicated. Sometimes you have to do the same computation 2 times. The first time you are just iterating to figure out where the hell your non-zeros are, and then layering out the data structure in there. And the next time I'm iterating over that to actually compute that. It's even worse because things like CSR format is contiguous in memory. So I can't even do it parallelly because I need to figure this. So sometimes I have to iterate 3 times. First time I need to figure out the entire size of the thing and in there, allocate that. And the second time parallelly go and set up the data structure in there. Third time actually copy the data. It's very, very bad. So part of that is, I think also we have created a set of data structures that it's not amenable to doing parallel construction of sparse in there. So this is where we are looking into some pointer-based data structure. So each parallel thread has its own memory. It can deal with that. So at least I can do some parallel construction. But getting parallel left-hand side is a non-easy task because if you just do simple append, it's somewhat easier. But sometimes you do insertion. So certain things I'm not even doing it in monotonic order calculating results. So that means I have to go in the middle and put something. So in those cases, what you do is you calculate a row in either dense or using a hash map in there, calculate that. And then once you finish a row, I have to do some extra computation to copy it back into my sparse format. So
yeah, it's a very different problem. I mean, as I said, a lot of sparse framework don't do that. Maybe we can take this offline, but I will suggest perhaps to look at our Comet compiler because it does generate sparse output for these
cool.
computations.
Okay. Thank you, everybody.